Hey everyone, and welcome. Today, we're going to dive into a topic that's really at the very heart of computing. But honestly, it's also a superpower for just thinking clearly. We're talking about algorithms and how they are pretty much the ultimate guide to solving problems.
You've been there, right? We all have. That feeling when you're looking at some massive, tangled-up challenge. Maybe it's a huge data set at work, a complex project, or, shoot, even just figuring out the fastest way to get through rush hour traffic. It can be completely overwhelming.
Well, what if I told you there's a systematic way to handle these problems? That there's a set of proven strategies that you can pull out and use to build a solution, one step at a time. That's exactly what algorithms are. Think of them as your very own problem-solving toolkit.
So before we can start using these tools, we've got to understand the foundation. First things first, what in the world is an algorithm?
Okay, that sounds a little formal, but it's actually super simple. Think of it like a recipe. You've got your ingredients. That's your input. You follow a very precise set of instructions. That's the procedure. And at the end, you get a finished dish. That's your output. It's just a sequence of steps to get from a problem to a solution.
Sorting a hand of cards is a perfect everyday example. You start with a jumbled mess of cards. That's your input. You follow a procedure, right? You pick a card, compare it to the others, and slide it into the right spot. You just keep doing that until, voila, you have a perfectly sorted hand. That's your output. See? It's that intuitive.
All right, so our toolkit can have a whole bunch of different algorithms in it. But how do we know which tool is the right one for the job? That brings us to our next big idea, measuring what actually matters.
Analyzing an algorithm is kind of like reading the specs on a new power tool. You want to know what it's going to cost you to run it, how many resources it's going to eat up. And while we care about things like memory, the resource we're usually most worried about is time. Basically, how fast is this thing going to get the job done?
And this really breaks down into two main things. You've got time complexity, which measures how much longer an algorithm takes as you give it more and more data. Then you have space complexity, which is all about how much memory it needs. For now, we're mostly going to focus on time, because let's be honest, that's usually the biggest bottleneck.
Now here's a key thing. An algorithm's performance isn't just one single number. It changes depending on the input. Like, if you look at these graphs, they show how performance can change as a problem gets bigger. We often focus on the worst-case scenario. You see that represented by that big O notation. Just think of it as a guarantee. It's saying no matter how nasty the input is, I promise the runtime won't be worse than this. It's how we make sure our apps don't just freeze up when we throw a lot of data at them.
Okay, so now that we know how to measure our tools, let's pull our first major design strategy out of the toolkit. This one is an absolute classic, a super powerful way to tackle huge problems. It's called divide and conquer.
The beauty of this whole approach is just how simple it is. Step 1, you divide the big problem into smaller, more manageable pieces. Step 2, you conquer those little pieces, usually by using the exact same algorithm again. And step 3, you combine all those little solutions back together to solve the original big problem. That's it. Break it down, solve the parts, and put it all back together.
And this isn't just some abstract theory. It's the engine running under the hood of some of the most efficient algorithms we have today. A super famous example is merge sort. It takes a giant messy list, keeps breaking it down into tiny, easy-to-sort lists, and then just merges them back together into one perfectly ordered result. It's just an incredibly effective strategy.
All right, the next tool in our kit has a totally different philosophy. It's called the greedy method, and it's all about one thing, making the best possible choice you can make right here, right now.
I love this definition because it's so direct. The keywords are best possible at each stage. So instead of trying to see the whole board, a greedy algorithm builds a solution one piece at a time. At every single step, it makes the choice that looks the absolute best in that moment, without worrying about what might happen later. It's kind of like a take the immediate win and move on approach.
And while it might sound a little short-sighted, this strategy is amazingly effective for a lot of problems. I mean, think about your GPS finding the shortest route. It often uses a greedy approach. At every single intersection, it just picks the next road that seems to get it closer to the destination. Or for something like the knapsack problem, it's about figuring out which valuable items to grab to fit in your bag right now. The crazy thing is that sometimes making the best local choice actually leads you to the best overall solution.
So let's zoom out for a second. We've defined what an algorithm is, we've figured out how to measure one, and we've looked at two really powerful ways to design them. Which brings us to our conclusion. You are now officially equipped with a foundational problem-solving toolkit. You're ready to build.
Just think about what we've covered. You now have the concepts to formally define a problem, to analyze how efficient a solution is, and to apply these awesome strategies like divide and conquer or the greedy method. Now, this is just a beginning, of course, but it's a seriously powerful start for taking on any computational challenge that comes your way.
And I want to leave you with this one last question to think about. See, studying algorithms isn't always about finding the single, perfect, flawless answer. Sometimes an algorithm that's super fast and gets you a good enough answer is way more useful than a perfect one that takes forever to run. So the real question becomes, out in the real world, when is good enough actually better? That's a key trade-off you now have the tools to think about. Thanks so much for watching.